So today I'm going to present some of our work in recent years. I kind of title it Towards Deploying AI in the Real World because that's usually what I'm passionate about. We want to write papers, but I want to make sure it also works in the real world. My name is Sernam. If you don't know my now, I'm actually a manager in Meta AI groups, and I manage a few teams there. We work a lot on computer vision is my main thing we work on, and we also work a lot on natural language processing combined with computer vision. A quick CV and bio about myself. Got my PhD in Maryland, 2005. Worked a couple of years as an engineer, and then spent 10 years at GE Research. And then, I was a director there, and then last 5 years, and currently I'm still at Meta or Facebook. I still call it Facebook. So I manage a few AI teams over there. My background is in computer vision, applied AI, multimodal, even NLP these days, right? So today's topic is I down-selected to have 3 interesting papers in CVPR this year that just got accepted, and then 2 from last year, ECCV. They're all premier computer vision venues, and so I thought they could be good topics to discuss today. The 3 topics are open and word, image semantic segmentation. Quickly, what is semantic segmentation? You have an image, you're going to say this pixel is actually belonging to a chair, this pixel belongs to the dog, and things like that. However, a lot of times these are all in a closed word label setting, right? You say, I only have 12 categories or whatever, right? So we're trying to march towards open word image semantic segmentation, right? And then the next topic I talk about is unsupervised image captioning. What that means is image captioning, if you guys work on the topics, you know that there's a lot of supervision needed. And so how do we move towards unsupervised? And then the last one is more on efficient model update. So a lot of models, I come from an industrial AI group background. A lot of models that is deployed in productions, they get stale because the data changes, right? The trend changes. Today I'm interested in Kardashian. Tomorrow I'm interested in some football teams or things like that. So the data actually change very quickly. So how do we efficiently update all these models, right, in production? Now the theme is that, right? I think a lot of these are all touching on computer vision plus language. I think these days, in sort of older days, not that I'm too old, but in older days, NLP guys and CV guys are kind of always in parallel stream, right? This day it comes together. There's actually not much different with the deep learning era and things like that. So you see that theme as I speak through my slides, all right? And then I'm going to talk a little bit about what I'm very interested in next. Subject to change, of course, because research topics change all the time. So the first topic I'm going to talk about is a paper in CVPR 2022 this year. We are very excited about this work. It's the first time we submit and the first time we got it in, very, very strong review. And Momar here will tell you that is very rare. Very exciting work. And I'll tell you the elegance of this method. Pay attention to that as well. The motivation is this. There's a lot of images that comes onto social networks. 3 years ago, it's about 50,000 images per second. Just let us sink in, 50,000 images per second. And this 50,000 images per second, you're doing classification on it, you're detecting integrity issue, whether there's nudity in it and all those things. And it's just huge load. A lot of these images is not going to stick to a certain closed word set of labels. Okay, because you're not going to just detect dog, cat, chairs, tables, and stuff like that. That is just toy, right? That's just toy example. We need to be able to detect anything we need, right? It comes in, I need to know this is a picture of a dog, but if it comes in as a picture of a Toyota Prius, I need to know that too. If it comes in as a picture of an auditorium, yes, I need to know that as well. All right, how do we get to that, right? That's the cool thing here. And then how do we do this large scale also, right? We're talking about 50,000 images per second, right? we need to do zero shot. That's what I was talking about, right? It comes in, I need to know it. Even I've not seen that label before, I need to know what it is. Okay, so I'm gonna present this work. And then I'm gonna say this way is even more challenging. It's not just saying an image is a dog or a cat. I'm gonna say in this image, this pixel belongs to a dog or a cat. This pixel, this is what we call semantic segmentation, okay? That's the problem. Now, I want to give an intro to CLIP, what they call CLIP. I'm sure some of you, if you're a graduate student in CV or NLP, you must know this. If you don't know this, you should not get a PhD. But CLIP stands for Constructive Language Image Pre-training. In the traditional sense, and then even now we call it traditional now because it's old work, last year's work, right? You take the CRS token of the vision, is a transformer usually these days, right? The encoder is a transformer, is a VIP transformer. And then you take the CRS token of the text and you assume you have image tags, right? So you have an image, you have a text, and you know they're paired together and you say, I want the CRS token, which contains the, you can think of the representation of the image and the CRS tokens of the text of this pair. You want their token to be very close to each other. That's what they call CLIP. Very simple idea, but what this authors of this CLIP paper did was they trained on such a huge scale. They didn't publish the data, but there's a group of people who try to create another similar scale, it's about 400 million. What my team has created was 2 billion, image text pair, right? So anyway, it's a very, very, very elegant idea where once you know how to align image and text into very close embedding space, what happened is that during inference time, you get an image, you get the embedding of this image from that CLIP model, and then you go to a database of text and retrieve the closest. Why can we retrieve image of text? Because now I make them close in embedding space. That's why I can use the image to retrieve. And guess what? If I retrieve a text from a gallery or database, that is what it is in theory, right? So for example, why is this zero shot? Why is it that it's open world? It's open world because I can now comb or sweep the internet of all the words in the internet, all the words, right? Cat, dogs, blah, blah, Tom Brady, Aaron Rodgers, I don't know who is football fan, UCF Knights, I don't know, right? Everything in the database, you can put it in a gallery. And he's gonna be able, the image is gonna be able to retrieve that text. And once it retrieves, you know what the image is. That is why it's open world. And sometimes we'll call that zero shot. Okay, so I want to kind of explain this very clearly. I put some equation here. I put some equation here if you're interested. So essentially, f sub v is actually the vision encoder, and then f sub t is the text encoder of the CLIP. Some notation here is the E and V. So usually you take the vision encoder, you take the text encoder, you don't just compare them directly, you put them through a encoder of CLIP called E and V, EV for vision, T for text, and then you do your influency loss. Some math here, I'm not going to go into a lot of details, but that's what it is. Very simple idea. Now the question is, what can this CLIP model do for us? So there's 2 experiments we ran on this using this CLIP model in terms of image semantic segmentation. Again, I want to repeat. Semantic segmentation is I take an image and know this pixel belongs to the chair. This pixel belongs to the desk. That's the task. Now, CLIP is trained on image level classification, not the pixel level. Okay? I want that to be very clear, all right? Okay, so can CLIP be able to do pixel level classification? That's the question here, right? So if you see here, I take the f sub v, which is producing this to this. Initially, the f sub v without a head is actually producing only this. But you can easily just create this t, which is the number of tokens, which is the patches, the number of patches in the image. Why is it easy to just modify f sub v, the f sub v head that produces tokens? It's because these days we use transformer. So everything is tokens. VIT is a bunch of CRS tokens plus all the patch tokens. Very easy. So nothing much to this, but this is an experiment we did. We take all this tokens, which is patch level in an image, and then we run an experiment to see how good Clip can classify it. And you can see that it's actually not very good. It's actually, this is our method, which I'm going to introduce later, but this is what Clip does. It's not very good. So they are clip to text alignment. Sorry, they are pixel to text alignment that Clip is able to do is not very good. That's the conclusion here. And you can see that it's not very good performance also, using a different version of VIT models. For those who doesn't know what VIT is, it's a very famous vision transformer models. Basically, it takes a CRS tokens, patch, you break the image into patch, pass in a transformer, do the multi-hit self-attention throughout the classification and things like that. Okay. So fact number one, we established a Clip does not do very well at pixel to text alignment. Okay, not image to text. We know Clip does very well at image level to text, but not at pixel level to text. Okay. Now, the second property that we want to look at is semantic coherence. What does that mean? That means that I want to see whether that the pixel can that are on the same objects comes together, has very close embedding space. That's what we meant by semantic coherence. We run a bunch of experiments, same thing. We take patches, right? And then we run an experiment to look at the cosine distance and things like that. And we found that it has very good coherence, meaning that you take the patch level, again, patch level embeddings from Clip, and you try to group them together because you know which pixel belongs to which objects, right? In the image, they actually groups very well together. You can see this Clip. It groups very well. Dino is another very famous vision model that's self-supervised. You can think of it like a self-supervised VIT. VIT is supervised, self-supervised. And they're supposed to be very good for clustering pixels, and they're not even as good as Clip in terms of this semantic coherence property. So what have we established? Anyway, if you don't understand anything, just feel free to stop me. We've established two things. Clip, right? Very poor at patch to text alignment. Very good at taking patches and clustering them together. That's what we established. So there's hope here. There's hope here that we can use Clip to do open world semantic segmentation, because Clip itself is open world, as I just trying to say, right? Just now, using a gallery of tags, you can go to retrieve and then it's zero shot. So what did we do, right? So we introduced a method called patch align contrastive learning, PACAL or something if you want to. So you see that we can take the patches, let me explain in layman terms. You take the patches, right? And then you add these patches and you group them together, you sum them together and use that in place of the original vision encoder. So originally you have the vision encoder embeddings here in this cosine similarity. Now you take this V, there's actually contains of a sum average, if you think of it that way, of all the patch representation. And that's it. We didn't do anything much. And then you just train this EV. That's it. You keep Clip frozen. You don't update in the training, and then just train this E sub V hat.
So in this thing, you assign the label to each page. Is that the idea? That each token get a different label, right? The semantics.
No. Well, you don't have the patch level label. You only have, as like Clip, you only have image to the text pair only. The same thing. You have nothing.
Yeah, that's what it, but that way you just assign one label to all whole image,
yes,
right?
Yeah.
One text.
Exactly.
But here you want to do the pixel-wise or page-wise segmentation.
Correct.
So, and that's why you're using pages and tokens.
Exactly. So you replace that, and you're still using the image to text pairing as a supervision. Nothing changes there.
But at the end, then how do you assign the pixel-wise labels?
Yeah, so we'll come to that in a minute. So during inference time, yeah, go ahead.
Yeah, I have a question like, so you said that VIT didn't work well, right?
VIT did not work well.
Yeah, so when you try to use the concept of VIT,
Mhm.
it did not give a good result, right? 2 slides ago.
Yeah?
Yeah, it did not give good result, right?
No, this is clip.
Okay.
Clip.
Yeah, so you're using clip and you are using the concept of VIT with clip, right?
So yeah,
Or
so
it's okay, right?
clip vision encoder is using a VIT, and then you have the text encoder. And then what we are doing is we break it down into, we take the patch token and try to retrieve the text. And it didn't work well. It means what it means is that clip, even though you can give it an image and it retrieve text and recognize the image, there's a cat in it very well, it could not do it at the pixel level, at the patch level. That's the problem. And this is actually a well-known fact, to be honest. There's subsequent papers that also found this out and things like that. So it's kind of interesting. Whereas it has good semantic coherence though, clip, meaning like you take clip, you use clip to represent all the patches because this vision encoder is a VIT, is a transformer. You have all the patch tokens anyway, and you try to cluster them, and it clusters very well. The patches that belongs to the same objects clustered together quite well. So okay. So anyway, this is our formulation, and the results are super good. We're very excited about this. This is a diagram. Unfortunately, there's this thing blocking, but this is a diagram that actually represents the whole idea here. Essentially, you see that you have the text. The text doesn't change; it's processed in the same way. But here you added our new cosine similarity, and then which is right here. And then the result is really, really good. You look at Propel, it's almost very close to the ground truth. And again, we did not label the pixel. Now, how do we do it, remember, right? That's the question. So during inference time, what we could do is that we can actually also take the patch tokens from the vision encoder, pass it to the clip, because it's VIT again, right? So it has this patch token. You take that, you go retrieve from the gallery of text. And once you retrieve it, you run a softmax to get all the classes together, right? And that's the result. And it's really good. And it's open world. We're very excited about this. And we want to deploy this into production. This is a CVPR 2023. The reviews are super strong. I think it's going to get a lot of citation, but that's beside the point. That's the first work. And it sort of set the stage for my presentation today is I really like work that is open world and very strong performance like this. And it's very useful. Why is it very useful? Right, so let's say in social networks, the image comes in. We want to detect integrity issues, right? We want to say there's a violence in this image, that somebody is stabbing somebody or that kind of thing. You can do supervised closed world label. You have to rely on method like this. And we know that where is the region in the image that the violence is happening, for example, just as a use case, right? Things like that. And then you'll see that even at image level classification, we're still better at clip in almost more than half the task. So clip is good for image level classification. Take an image, retrieve from a gallery of text, right? Now we added this thing where we can take a patch from the VIT, retrieve the text, and do our semantic segmentation, softmax over the patches to get the right segmentation. But you can, of course, do image retrieval, right? And it beats clip in most of the tasks. Not all, some is still not as good, but it beats clip.
So this clip was your pre-trained, publicly
Pre-trained,
available?
yes.
You didn't do anything?
We didn't touch it. And Mumbara, I think, bring up a very good point. We don't even need to train like how clip was trained. You just train that little vision embedded after the encoder with our new Pascal PACL loss function, and that's it.
So in VIT, the patch size is fixed, right?
You fix.
So did you have to change the patch size?
So VIT gives you different batch size. So VIT 16 will be 16 by 16. VIT 14 is 14 by 14. So we just based on And it's good enough. I mean, it's not that big, 14 by 14. And you may get into a little bit of the contour has a little bit of a, roughness there, but I think overall it's pretty good. But we are very excited about this one because it not only is very good for open world semantic segmentation where we can localize something's happening in the image, it's also even beating clip at image level classification. And that's the beauty of this method, right? So I'm going to kind of move on to the next topic, but any questions so far? This is the first topic. On this, no? Okay. Now, the second thing I want to talk about is an ECC 2022 paper where the goal here is that we do a lot of image captioning, to be honest. It's very important to do image captioning because if an image comes in, you want to know what it is, what it's doing, or even a video comes in, you want to know what it's doing, and then you can actually react to it, right? And a lot of them, is for integrity use cases as well. Or, for example, John likes soccer, and I can detect this image. There's a soccer game going on in the image or video, and I can caption and say, Lionel Messi World Cup, blah, in this video. That help us make recommendation, right? If you're a football fan, I kind of at a loss, Dolphins or whatever, right? Right, or Buccaneers, right? And then you like that kind of videos, and it helps us make recommendation because if we can caption that video, we know to recommend that to you if you are a Buccaneers fan or something like that, right? So captioning is actually a very important task. And there's two things to build captioning, right? A lot of them has to annotate. So you take an image and then you painfully annotate it. MS Coco, all those data set does that. You open image, it does that, right? They annotate the image, right? Painfully, you sit down, you spend upward of millions of dollars labeling these images and stuff like that, and literally, right? And so, how can we do it unsupervised? That is the question we want to solve. There's a ECCV 2022 papers. Again, unfortunately, this thing is blocking me, but essentially the idea is very simple, right? So. The idea is very simple. The idea is usually what you have in terms of image captioning in supervised setting is you take an image, you get somebody to write it down, and you do it a million times, right? Now, instead of doing that, what we do is we take a sentence, and then we break it down into nouns. What is nouns? It's objects, right? So, Tom Brady is throwing a football. Sorry, I keep using that example because it's Florida, so Buccaneers, right? Yeah. So Tom Brady is throwing a football, right? The action. So there's a football. There's a Tom Brady, is a now the person and things like that. And then we take all this, we go into a corpus of images unrelated to the text. They're not related, okay? They're not related. Unrelated to the text. I take all these nouns and text. I go to my corpus of images and I look for person. I look for football. I look for whatever is in the sentence, and then I take those objects in the images, a person, a football, and whatever, or even a background, football field. And I take those segment regions out. And then I take this sentence and I say they are a pair. And then I take this pair and I train my captioning model. Does that make sense? So there's no supervision here. Now, but what do you need? You need to know in the image where the object is, where the person is, and cut it out. Now, I say cut it out. We don't literally cut it out. Everything is transformer. You just need to get the representation of the object in the image and use it as a token, and just input it to a transformer. So you're not really making an image with all this cut and paste together. I just want to be clear about that, right? Because these days everything is transformer, right? So that's the idea. Oops. That's the idea. Oh, yeah. So that's the idea behind this. Any question? Okay. So how does that work, right? Because it's very kind of, if you think about this idea, it's a little bit weird, right? It's not the objects are not from the same image. It's basically from different image. But what's the advantage of that? The advantage of that is if you were that, so the state of the art in unsupervised image captioning does the same thing. They do the same thing. but they look for objects in the sentence, but they require them all to be in the same image. You see my point? We don't require that. We just go to the corpus. I find a person here, I use that person. I find a football here in this image, I use that football. Right? I cut it out, I represent it as token and stick it into the transformer. Okay. How would that work compared to these guys who require all the things in the sentence to be in one image? Is that clear? Is that clear? All right. Now the question is, why do we want to do that? Because of object coverage. You can see here the object coverage is very important. Unfortunately, in this blog, you can see that at 100% coverage, all the metric we perform way better if you have 50% coverage or 20% coverage. And if you take some of these state of the art, this is on the state of the art, we muck around with their code a little bit to reduce their coverage. And you see their best coverage was at 47.5 when they need to find that one image. Okay. But we muck around their code and reduce their coverage, and you see the performance drop by a lot. We're talking about 32%, 42% kind of drop. Object coverage is very important to do this unsupervised image capture. Make sense? Very clear, right? Hopefully, okay. So that is the importance of object coverage. And the reason we're doing this, where we go mine objects from different images, is to increase this object coverage. And our object coverage is almost always 100%. Because very simple, right? You got all the images you can find all objects in this, you're probably gonna hit 100% most of the time, right? We can also do this with not just objects, right? If you know how to detect relationship in sentence, and you have a relationship detector in image, such as a scene graph, like you know that a man is riding a bike. You know the man and the bike has a relationship. And the sentence has that. And then you can use that relationship to mine these objects too. So that's what it is. Forget all the math, but that's what it is, right? In layman's term. You can also extend it to non-English, right? How do you do that? You take the English language, you translate it. There's a lot of translator out there. You just translate it, all right? And then the same thing. Now you have that Chinese or Hindi or French or stuff like that, and then you find all these nouns, and then you go to the translation English word, and then you go find that thing again, because most of the object detectors are based on English, unfortunately, but you can use it on non-English, and you do that, right? And we'll show some results on that. So our results are very, very, very good, very, very. So our methods beat, so 16 and 11, because I think it's 11 here, beat their result overwhelmingly. So the previous state of the art in unsupervised image captioning, using the kind of similar method, but constrained to one image, okay? We beat them, easy, all right? And then here is ablations on if we add attributes, relationship, and add object plus relationship plus attribute, and how do we perform? So relationship, an attribute, like he's wearing a blue shirt, so you're going to look for blue shirts, right? And things like that. If we can detect the attribute, it improves the captioning much better. You can see some qualitative example. This is our example here. I'll put here. This is human annotation. This is some of the previous state of the art. Our language output is much richer, better, more descriptive, in a qualitative sense, because we have so much object coverage, it's almost always 100%, we get much better captioning. So very strong results. And then this is some of the Chinese ones. I think this is French. We did Chinese and French because there's some data set on French, some data sets on Chinese. And then you can see some of the results on the quantitative results here as well. So this is the second piece of work, right, where we talk about this, right, where we have motivation to take image captioning and change that into from a supervised to unsupervised setting using object detector that has been trained before, right? Now, there's some criticism from reviewers where.
That's what I was going to say. But The object detector will train supervised.
Exactly,
It's not
right?
really-
There's one of the reviewer to say that. Here's the thing. We don't know what we don't know at the time when we wrote this paper, right? But lo and behold, what happened? glib came. glib is an object detector that uses CLIP to do open world object detection. And it comes very close to some of the faster RCNN object detector. So now you don't even need supervised object detector anymore, right? So just to answer Mura's questions, the first work I present was using CLIP open world properties to do image semantic segmentation. There's another work that came out called glib.
Yeah, I haven't seen that. When did
It's
it-
by Pinchon. I don't know. I can send it to you.
Oh,
Okay. Where he, instead of doing image segmentation, is object detection with CLIP, and it's open world. And lo and behold, now you don't even, I know the reviewers are talking about that too, and then give us a hard time. This one was like too strong one rejected kind of reviews. But lo and behold, move forward to the future. We have glib, and glib was performing very strongly, open world, unsupervised. Now, of course, then you ask, well, CLIP is still supervised. But you know, they train it already. Why not use it, right? Why not use it, right? So anyway, this is a very, very strong result, and I want to motivate this in this sense, right? Like a lot of time we use this on social networks, right? Where we say this image is this, we can make recommendation as I was explaining in the beginning. And we have motivation to take this and actually move into production right now and to use this for production. Okay. So there's the third work I'm going to talk about, which all along the themes of trying to deploy AI in the real world and things like that. And this is a ECV 2022 paper called Visual Prompt Tuning. So the problem here is this, right? These days, all the pre-trained model is huge, right? We're talking about the latest ChatGPT model is 320 gig. You can't even load it onto one GPU these days. It's 320 plus gig. They are huge, right? And a lot of time, practitioner would still take this large model, and they have a task. Let's say their task is to do recommendation. Their task is to do search engines. Their task is to do integrity detection and things like that. They'll take all these models, and then they'll fine tune on top of these models. And then they'll store their models. Now, guess what? So now let's say in a company, there's 100 teams using this models, where they take these models, they make a copy of it, and then they fine tune it. We ended up with 100 copies of these 320 gigs models, and all having a little bit of fine tuning on top of it just for their tasks. And that is the problem, the first problem we have in the real world. Of course, the second problem is they also fine tune it in this way. They just update a full fine tuning, right? So they have their task, they have their labels, they have their supervision, they'll update the whole thing. That's why we call it full fine tuning. They fine tune the backbone, they don't keep it frozen and things like that. And it's very inefficient. I'll give you a general idea. Some of this model that we want to deploy sometimes takes 6 months to a year. Okay, so you have a new model, you're very excited about it, the researchers are very excited about it, say, I want to deploy it, right? Let's see how it works, right? It works very well and stuff like that. And then from the point they build their model, it takes another 6 months to a year to deploy that model into actual usage, right? And guess what? 6 months and a year later, with the way AI field is moving, that model is obsolete already by the time it gets there, right? So that is the problem too. And we don't want to do this full. So some of the LLM model that we built internally took 4 months, 4,000 GPUs to update. And that's just to get to the new model. And then you have all the production complexity that you need to muck around with. And then by the time you're done, you spend 4 months, 4,000 GPUs. Now you do another 6 months, so it's 10 months. And then you have that model ready and things like that. That is the issue we are also trying to fix in this world. So 2 issues, right? How can we update models quicker And then of course the model zoo storage issue, right? You don't want to be storing 100 copies of ChatGPT. That is just not very efficient. So that's the problem we're solving. So I'll motivate this work by a couple of things, right? There's a lot of work in NLP that's quite interesting. Okay, one of these one is called prefix tuning. So the NLP guy, we used to think that the CV guys like us and Mumbai are smarter than NLP guys, but actually maybe they're also quite smart actually. So they found out that if you take this, a pre-trained model, and you want to update it to a certain task, right? You don't have to update the whole model again. You just need to add some little parameters, they call it prefix, to the layers, right? The output of a layer, yeah, there's some prefix up, and then the input of the layer. And these prefixes are very small, very small. You don't change this huge backbone model. You don't touch them. You keep them frozen and everything, but you only add this prefix to it. And then you just train your task to train this.
So this is also called adapter or something?
There are also different versions of this called adapters, and then this is prefix. Adapters are a lot different when they actually go inside and change the transformer layers a little bit, the loss function and stuff. But they are all very similar ideas. Here, you don't touch anything in the transformer, nothing. You just add something to it. You append or you prepend to it. And then you just freeze all this, update this. Does that make sense? So the NLP guys came up with this idea and it works very well. It works very well. And sometimes they found that they can outperform full fine tuning, which is the whole, updating the whole models, right? But rarely. So here's where computer vision and NLP sort of differ a little bit. When they do prompt tuning, they cannot really update. They cannot really beat full fine tuning very consistently. But what our work found in this for CV tasks, it actually beat full fine tuning quite consistently. Okay, and I'll come to that in a minute. So what we did is this, right? We follow this idea, but now we are in the CV domain. So what we did is we also add prompts to the input to the layers and stuff like that. And we don't touch anything here. We keep them all frozen, and then we just update the head and the prompts, right? Now there's a different version of it. You can add it at every layer. So there's what we call VPT deep. VPT stands for visual prompt tuning. It's called VPT deep. And then if we only add it to the input layers, only just a small number of prompts, we call it VPT shallow. Okay, so these are two terms. So I'm going to talk. I think I talked about this quite a bit already. And one of the things is that actually by freezing models and only updating the prompts, there's also another added advantage. When you update the whole model, right? There's an effect called catastrophic forgetting. So the model actually forgets what he has learned when you update the whole model. I'm sure folks who work in this area know what I'm talking about. Like, they call it catastrophic forgetting. So full fine tuning has the issue as well. So we also realized that a lot in our settings, right? A lot of models, if we do a full update, we need to pull the data from the past to train it together with the new data to fully fine tune it. It's a very laborious process. So we actually do a lot of continuous learning, but that's another story where you don't want to forget all this data. But by freezing the backbone and updating only the prompt, you actually avoid forgetting what the model has learned in the past as well. So this is one of the things that I want to talk about here. And then the rest, I think I covered them already. Here's a slide where I talk about what we compare with. We compare with just updating linear layers, so single linear layers for the classification head. We also compare with partial K, so we only fine tune some layers of the backbones, partial K. NLPK, so we also utilize a more than a linear layer, NLP with K layers. So these are the methods we compare with. We also compare with site tuning, which is a method where they actually added something on a model on the side, like an auxiliary model, to tune the thing without updating the backbone. So they have a site tune. This is actually Jitendra's work, if you know Jitendra. and then bias, and then adapter, which is what Mumbar was talking about. We compare with all this benchmark. The downstream task is the SGVC, and then the VTAC. This is about 24 tasks in total. So those are the downstream tasks. So here's the results here. Very strong results. VPT deep actually beats full fine-tuning on average, which is a very, very big results for us, especially in our setting, as I explained. If I only need to update the prompts, keep the background frozen, now the company or whatever, just need to keep one copy of the big backbones, and you're just keeping the different teams are just maintaining their prompts, which is way, way smaller, like 100,000 times smaller, right? And even with that, you would think that we will not beat full fine-tuning. We did. We beat full fine-tuning. Now, if you break down the tasks, we didn't beat them on all the tasks. We beat them on 20 out of all the 24 tasks, but on average, we beat full fine-tuning. This is very interesting result because you see that this is the amount of storage that we need for the prompt is really small compared to storing a copy of the big backbones for every team throughout the company. So because only one backbone is needed. And then you will see that here, we show some results, and you see that indeed, for VIT 16, we are really dominating also the full fine-tuning as well. Okay, so these are very strong results because who would think that this, because even in NLP work, people who did a prefix prompt tuning, they did not conclude they could beat full fine-tuning.
So what's your insight? Why is it working so well for the vision?
We are still studying it. I actually don't know. So this is very empirical. We are very surprised by the results ourselves. If you want to ask me an insight, I think language is probably more unstructured than vision. Maybe I don't want to say that. I think language, there's a lot. Language can be in any form and format, right? I'm a man. Man am I? You know, Yoda. All right. You know, I'm running. Running am I? And then people say it differently. I'm walking fast and things like that. So I think it's much more unstructured than vision. Whereas vision is an image, 224 to 224 grids, right? And that may be why. I don't know.
One would think that it's easier to define what the prefix means in language than in vision, right?
So you're saying?
I mean, in case of language, it's clear what the prefix does, right?
Yeah.
It puts at the beginning of
Yeah.
the sentence, right? In
Yeah.
case of, well, you have some kind of a tokenization to the VIP, but that's not quite as obvious what the prefix means.
Well, for us, the prefix is just a set of parameters. We don't. It's just.
Does it make sense that it's a prefix, not a postfix?
Yeah, we'll come to that in a minute. All very good question, which we also don't know why. But you see this pre-pen works the best. So you're asking a question, why do you put it in the front and not at the back, or not in the middle, and things like that? And we did the ablations too. Pre-pen is always the best. Now, if you ask me why, I can explain it in a way that does not explain it. Okay, so if you look at the VIT transformer, right? They put the class CRS token in front, and then all the patch at the back, and then they turn it, and then they output the class and stuff. And the class, the CRS token is always very strong representation of all the patches, and that's why people just use the CRS tokens. Now, does that explain it? It does not. But VIT also sort of tells us the same thing, that pre-pen token there is very representative thing. So I don't have the full, analytical explanation, but I think empirically, that's what it is. Any other questions? So yeah, so this slide is just to a lot of these questions is, yeah, prepenning we found that prepenning the prompt is the best, and so I thought this could be interesting as well. And then we did run it on swing, which is a hierarchical transformer. If you know what swing is, they actually have a different scale and stuff like that. Kind of like ended all of the ideas, and we did not beat full fine tuning. Okay, so on VIT we did. On swing we did not, but we still beat most of the other fine tuning approach, but we did not beat full fine tuning. You see, 53, 59, 54, 86, 86. So we did not beat them. Where swing is kind of a hierarchical sort of transformer. It tells us something. We're still, yeah.
But so that's interesting, right? So swing that better than VIT, right? That's what they have the more price. So you're saying that you swing and you can beat with,
Yeah, you can.
So that's interesting. It's dependent on the transformer, which transformer you are using.
Yes.
Yeah. Okay.
But I still cannot give you an analytical explanation. We're still thinking about it a little bit. In fact, we're using this quite a lot now with all the LM stuff that coming out. I'll talk about that in a minute, but
so the one criticism about these, prompt and these the other names is that how big is it? Because if you apply, if you use lots of them, they itself are very heavy. What's the size of this prompt like?
We have used 128 to 256. But you're right. In LM, you at least need 400 tokens as input. So you're talking about 400 times, let's say 128, 256 is big. So in actual settings, loading some of this takes 5 minutes just for one inference. So it's pretty heavy. And this is a problem we need to solve. Because we can talk about how good this ChatGPT model, this big model is, this transform model is, but until you can load it like that, it's never going to be useful. I mean, you can run offline jobs, right? You can process the image offline and things like that, but even that will take forever, right? If you're talking about 5 minutes per inference. All right, so let me move forward. So I just kind of want to finish up these 15 minutes for discussion. So I think we are about at the right time. I think what I presented today is number one, right? We use vision language pre-training, right, for image semantic segmentation to achieve our open world objective. And you'll see that the team is this language involved here as well, right? In the second one, we talk about unsupervised image captioning, which is language as well, right? There's an interplay between image and language and things like that. And then in the third work, we talk about borrowing some of the NLP prompt tuning insights to vision. And to me, the research direction for me moving forward is the combination of large language model and computer vision, right? Now I can give you a couple of how I'm thinking about this. So there's a thing called React. I don't know whether you guys are aware of React. It's a very interesting thing in NLP where you can actually give him a template. For example, who is the most popular football team in Florida? And then you can give it a template. Should I ask the follow-up questions? And then so you give it a lot of this prompt template, and the model actually knows how to step through and say, if you ask me a question, I can reason about, do I need to ask a follow-up question? Do I need to go run a search engine and things like that? That's what they call React. This is very much aligned with what they talk about in chain of thoughts. So you're reasoning through step by step, right? Who is Yan LeCun? And you're reasoning it through step by step and things like that.
So is the ChatGPT doing that or not?
They are not doing that per se, But of course, I cannot say for sure because they never released the model. So
Yesterday, they put a paper on archive called Visual ChatGPT.
yes, I knew about that paper. Once it came out, I got all the alerts coming into me. That was from Microsoft. If you're talking about the Microsoft paper, yes. So that paper came out yesterday night. I got a lot of ping, 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 and that's exactly what I'm talking about, right? If I give you an image of myself, and I say, model AI, make me look good like Tom Brady. Boom. So you go in, the model knows how to step through. Okay, let me run a diffusion model, right? To make Sernam looks good. He doesn't look that good, right? So blah, blah, and then make it skinnier and things like that. Generated. So you utilize the power of this reasoning that ChatGPT had, but for computer vision. That is what I want to kind of pursue. In fact, what I'm pursuing right now that I'm very excited about. We have seen very positive results and on that front, and I believe it could be groundbreaking. It could be groundbreaking. So I'll leave it at that because I don't want to say too much. The other one I'm kind of more passionate about is neurosymbolic or codecs, right? So think of it this way. So in clip, you use natural language to ground the images, right? What if you use code to ground the images? Right? If you use code, code to ground image. So the NLP guys does this very well. They actually train codecs, what they call codecs, right? So they are able to take a, let's say you say, can you write me a program that jumps over a chair and then roll under the table? I don't know, I'm just making it up on the spot. And the OpenAI codecs will actually spit out Python code and say, for t equals 0 to t equals 5, blah, 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 and you spit out all of the Python. It's pretty amazing. Now, think of it this way. So I put this here. We just submit this to ICCV, so I put this here. If I have a code that specifies what I think this video is doing, and that code could be pretty general, I can actually ask a model to spit out or predict fine-grained events that align with my code-based specifications. That's one usage of it. What does that mean? So for example, Mugen is, sorry, there's a data set called Mugen, which is like a game where this thing is jumping around. I say, if the specification is Mugen is walking 2 steps, like collecting a coin, and then getting killed. Okay, I have the video, I have these specifications. I can actually take this and the video and teach a model to output the intermediate events that leads to this final code-based specifications. So I'm going to stop at that. So I think that codecs is going to be the next thing we can do for computer vision, number one. And I will tell you something. ChatGPT, the reason that ChatGPT is so able to reason, what I found is because it was not only trained with natural language, it was trained with code. I found from some colleagues at OpenAI. So they actually train with code. And I think we can apply this to computer vision.
But even now, I mean, you can get a code in Python.
Yes. You can write natural language and it'll give you code. Like these days, you don't have to work. You just, my boss asked me to write some program. I mean, just boom. Of course, it doesn't compile, but there's a lot of bugs. You got to fix it. But it's amazing where we are today, right? So I got my PhD in 2005. So let me close this up. Long time ago, I mean, Mubara got even 20 more years ago or whatever. We cannot imagine what we have today. You guys are in a wonderful world, I tell you. Like back then, we are doing normalized cut for segmentation, and Mubara know what I'm talking about. But it doesn't work, and then you got to slide the threshold and hope it works and pray to God it works, right? And things like that. These days, we have this powerful model that's doing amazing thing, and I've seen these changes for this years, and I'm just very, very excited about these things. And I think we have a lot to do here, and I think we can learn a lot from NLP guy. And that's my conclusion. Okay, that's it. Thanks. Okay. Any questions? 10 minutes. Yeah. No questions?
I have a question. If we can start first, like from Zoom.
Please. Go ahead. So you want control?
No, I can hear you, yeah.
Yeah.
Go ahead.
Maybe your thing is muted. Is it there? Can you hear us? Who is asking
Yes,
questions?
I can hear you. Yeah. So thank you for the wonderful talk. I'm Yogesh, and I'm at CRCV at UCF. So I have a question about the VPT, the last piece you presented, and that's really very interesting. How you are tuning those prompts, right? So what I wanted to know is, because you're trying to adapt like to different downstream data sets, right? By attaching those prompts. So
Yes.
do you think there can be a way like those prompts are like shared across multiple architectures specific to each data set, right? Because the prompt should be attached to data sets, not models. So do you think that is like something which can be made possible?
Yeah, so great questions. Because it was recorded, I did not talk about what we are doing with it internally. But what we did deploy this technology and works very well, so surprisingly. And then to your question, Yogesh, is that we created a bunch of prompts in a zoo of prompts. So we just train prompts for different tasks, and we created like hundreds of prompts in a zoo. And the prompts are very small, so it doesn't take a lot to store them and stuff like that. And then what happened with that is that for product teams and downstream teams, when they have a certain task, we don't even need them to train the prompts. We actually do this very similar to what we do with attention mechanism, and just go in to mix and match the prompts together for that task. Does that make sense, Yogesh? So that's even model agnostic. We say, what's your task? What's the model you have? And then we go into that model, the prompt zoo, and then we use an attention mechanism, key value, and you multiply them, and it's basically clustering, right? And say which set of prompts are the best for this task. Does that answer your question?
That's interesting. Yeah, thank you for sharing.
And in fact, at the same time, Google published also a paper talking about this. They also found that you can do visual prompt tuning. And luckily, we published at the same time. Otherwise, I probably cannot get the paper published. But they also found that you can do visual prompt tuning. And they took it a step further and set the problem in continuous learning. That is exactly, I think, what you're asking. And we were very fortunate that the two papers came out at the same time and got accepted. If the reviewer has killed us paper, then this paper wouldn't exist. So.
Okay, that's great. Thank you.
I was interested about your work on the background business segmentation. So what I understand that you are leveraging the clip images, right, which is trained on this large scale vision language data set. So I was wondering, in principle, that will work at your result kind of shows that it works in the natural images, segmenting different concepts and stuff. But what happens actually if you go to specialized data sets, like medical segmentation, or let's say we have some IC boards which has, you have to segment different ICs. I think that the concepts are fuzzy because it's the granularity at which you want to define is kind of dynamic. So, like,
I see.
A model like yours will probably struggle there, but is there any work you are interested or think of developing later on which will do this adaptation on the fly?
First, I would say I don't think it will work like that. They are all natural language and natural images. So I think There is some work going on with Kunal Ramin Zabif. I don't know whether you know him. We are working on some survival analysis where they are looking at X-ray images and then predicting when it's gonna something, some treatment, and then predicting when the patient is gonna and not things like that. So we have not applied this yet, but there are some thoughts about that a little bit. But it will be hard because I don't think CLIP is trained for medical type of images, to be honest, even if you talk about geospatial images, right? Which the IR power guys will be very interested in, right? But it'll be very interesting to apply that to see whether we can do something there.
Basically, my question was on the line. Let's say you have a generalist model like this, how do you tune it for your specialized task?
I don't think it could. That's what I'm to answer is. I don't think it could, but I don't know until I run the experiment. Because I think the nature of the modalities are very different. I don't consider medical images or geospatial images the same modality as natural images, to be honest.
So maybe you can do domain adaptation, right?
Maybe you can use visual prompt tuning and see whether you can tune that. First of all, unfortunately, I don't have a very good answer for it because I've not done work here. We are trying to do something with Cornell on this. So I can't answer you very authoritatively, unfortunately. Yeah. But that's a good idea. I think it'll be very helpful though. So we'll see. Yeah.
I have a question.
Yeah.
So in your conclusion in the future work, and you talk about the borrowing of the intelligence from the natural language into the vision learning.
Mm-hmm.
Also, you just also mentioned the ChatGPT, learning the great reasoning capability from the code language.
Mm-hmm.
Does that mean in the future, a lot of machine learning tasks can also follow such a style? I mean, try to extract different intelligences from different modality of the information and transfer the knowledge into that specific task. But of course, we might need a model form, right?
I mean,
sounds like
it's definitely possible, right? I mean, some work that's going on that I knew about is to train a video clip, like a clip, but for video, for audio even. And also you have I think it's definitely possible. That's a quick answer. But I do believe this. I believe language is the grounding. Now we can talk about language in different form, code, English, and things. But I do believe that language is always the grounding because that's how we human are. We communicate with language, and I believe that's our grounding. And take that to transfer that learning to other modalities is how I think about this. Now, I think maybe what you're asking is that can audio be grounding the other modality, for example, right? Well, then the question is, does human do that? I don't know. I think we don't do that. I think we more do it with language, right? I say, I want you to do something. I use language, right?
Are animals which don't have language?
That's true.
Can do vision. Animals cannot do language actually.
That's true. That's true. So you got me there. So like I know bats. They use echolocation and things like that. So I mean, it got me there. This is a very philosophical question. So yeah.
So this Chomsky wrote an article last week in the New York Times. He says all garbage. This language model.
Oh, language model garbage. Well, I mean, there's nothing magical about it, right? It's
No.
I mean, contrastive learning or autoregressive learning is not a new thing, right? We in the old days we learned Markov model. That's more autoregressive, right? And things like that. So I don't think it's new, but I think what has happened in the last 10, 20 years is the hardware has really progressed and we can train so much data on it. And there's so much data. I think that's what, I don't think the technique has changed like too much to be honest.
I think the main thing is that it's a very different way to look at the language in vision.
Yeah.
Compared to this traditional Chomsky.
Exactly.
So it is good, I think.
Yeah.
It's good.
All right. Thank you guys. Thank you guys for coming. Appreciate it.
Yeah.